G'day, it's Prezzo back in the shop. Today I'm working on a project that I started a while ago. This is a tailstock tap holder. I bought one of these Jacobs chucks with a B18 internal taper, and I machined up this component here with the matching taper on the end. And the idea is that you can jam the chuck onto the taper, and then this shank fits up inside, and you can put the number 3 Morse taper in the tailstock of the lathe, and you can guide a tap and keep it concentric with a spindle. Now, the thing is, this part that I made on the lathe looks lovely at the moment. It's just been polished and it's just mild steel. Now, I can guarantee in about a month's time this is going to start to corrode, and what I want to be able to do is carry out a process called parkerizing, or a Parker phosphate coating. And I've recently purchased the chemicals to do that. Problem is, you need to heat these chemicals up to a very narrow range to make them work effectively. So that's what this video is about. I'll go into the parkerizing process sometime in the future, but for the moment I need to be able to make a way of controlling the temperature of a liquid to a fairly defined accuracy. Now, I purchased 2 of these for use in the shop, and these are great for heating up anodizing solutions or for boiling anodized parts after they've been dyed, and I often use them for heating up glue and that sort of thing. The problem is that although they have a thermostat on them, the thermostat is very difficult to control. What happens is you set it to a temperature like a simmer, and then the temperature overshoots that, so you crank it back a little bit and then it sort of goes off the boil, and then you find yourself continually fiddling around with this thermostat to try and get the temperature that you want. So there's quite a lot of thermal mass in this hot plate too, which makes it even more awkward. So what I need is a way of putting in a PID controller, a temperature controller, between the mains plug for the hot plate and my power in the shop. And that way I can leave the thermostat set to its full temperature and then let the PID controller do the rest. So let's have a look at how that might work. This is a PID controller. You can buy these on eBay as a kit. They come with a temperature probe and also a solid state relay. They are pretty good for what you pay for these, and they allow you to set a temperature. The sensor will then measure the temperature of whatever fluid or gas that you're using, and then it will send a signal back to the PID controller, and it will switch on and off a relay to control the heating element through the solid state relay. Now, the probe itself is designed to go into something like an oven where it's using hot air to measure the temperature. I want to be able to put this into a solution or a fluid. Sometimes those fluids are alkaline, sometimes they're acid, and there's no effective sealing on the back of this probe. This is a stainless steel braid which is just protecting the wires inside, and down inside here there's a thermocouple. Now, any moisture that you get down inside that is just going to sit there, and it's going to cause corrosion issues and problems with the insulation and so on. So what I need to be able to do is to somehow make that waterproof or fluid proof so that we can put it into the solution and not have problems with moisture wicking up inside this braid. So let's have a look at what I've got in mind there. This is a piece of solid drawn stainless steel tubing. It doesn't have a seam, seamless. This is the probe that was supplied with our PID controller, and it's a fairly loose fit up inside that stainless steel tube. And this is a fitting that I've turned on the lathe. It has a hole in that end, which is a fairly snug fit over the end of the probe, and then the shoulder that's been turned on this slug of stainless steel fits up inside that stainless steel tube fairly tight. So the plan is to silver solder all the way around that joint between the tubing and the fitting that I've made on the lathe, and then later we can insert the probe down through the open end of the tubing, and by smearing that with thermal paste we can make sure we get a fairly good thermal pathway between the liquid that we're measuring and the tip of the probe. At this end we want to make sure we don't accidentally drop it into whatever solution we're heating, so I'm going to fill the end of the tube with epoxy or hot glue, and then we'll put a heat shrink tube over that as well, just as an insurance policy. So that's the plan. So we're going to go ahead and make this and then see if we can control our hot plate using our solid state relay and our PID controller. This GP or general purpose silver solder flux, and we're just going to put a bit of a coating around that shoulder. It's a good idea to put this between the surfaces rather than just smear it on the outside, because this stuff will melt and flow and form a barrier to stop oxides forming, and oxides are the enemy of any soldering process. So we're going to put our cap inside the tube. Okay, so we're going to hit that with some heat, get that up to like a medium red, and then we'll flash our silver solder right around that joint. Alright, so it's going to use a propane flame here to get the temperature up, and we're going to run a bit of silver solder flux around the end of our brazing rod as well. We're just using the fire brick here to keep the heat around the part, so not losing so much heat. Need to concentrate the flame on that solid stainless steel tip as well. It's going to take more heat than the tube to get up the temperature. So it's starting to get toward the temperature we want, like a medium red. So the important thing here is to get a really good bead of silver solder right around that joint. Doesn't look terribly pretty yet. I'll go and clean this up. Just remove the oxide with a Scotch-Brite wheel. Just clean up that joint. So what we've got now is a solid tip on that tube with a pocket inside, just the correct size for the end of the probe. Okay, the thing we have to be careful of here is that we get this probe, the tip of the probe, in thermal contact with the end of our stainless steel tubing and the cap. If there's any sort of air gap there, we're not going to get a quick reading. It will eventually heat up to the correct temperature, but we want to have a quick response time. So this thermal paste should give us a better pathway between the liquid that we're measuring and the tip of our probe. So I'm just going to smear a whole bunch of that on there, and right, so we're going to go down in there like that, and we're just going to make sure I push that right down as far as it will go. Now in hindsight, it would have been better to probably put that thermal paste inside the tube somehow right at the bottom, but I'm going to try and clean this as best I can. So what I want to do next is get some hot glue inside the tube. Alright, I'm going to try and get some alcohol on that and clean it. Just remember, this is the best thing in the world for cleaning out something like that. It's balsa wood. It's sort of soft and it's porous and it absorbs stuff. So we can use that to clean down the inside of that tube. And the reason why I want to get that clean is that I want to be sure that the hot glue is going to bond properly. Alright, it's coming out pretty clean. Alright, I reckon I got that as clean as I'm going to get it. So we're going to try and squeeze some hot glue down inside there and get that wire more or less central. Alrighty, so we got a nice bead of hot glue down inside there now. Okay, so we'll get our heat shrink down over that joint now. We'll get some heat on that. Okay, one hopefully waterproof temperature probe, and the next step is to get this hooked up to our PID controller. We need to get the controller into some sort of a durable case with its solid state relay and make it look pretty. So let's check that out. Well, pilgrims, here's some of the hardware I've been collecting to do this job, and what I really needed was a case to put all the electronics in. And I had a look at some plastic cases, and I don't know, they just looked a bit flimsy, and I wanted something that was going to be durable and robust, and if I dropped it on the floor, which I do quite often, I didn't want it to all crack open and spill its guts all over the floor. Now I had some of this aluminium square tube. It's 100 square, 100 on each side, and I had a piece that was just the right size to take the PID controller inside there. There's enough room to have the solid state relay underneath that, and I can fit an end plate at both ends. I've got some little plastic feet just to finish it off, and a handle. And I like to have a handle on things so you can just pick it up and put it on a shelf instead of having to grab it with both hands. So what we need is an end plate to close off both ends of that tube. Now I've already made one of them, and it's just a straightforward piece of sheet metal that's been bent and cut to fit, and that's going to go at the front. There we go. So that's going to fit in there like that, and I'll be able to fix that with a couple of self-tapping screws at the side there. This will need to have a rectangular hole or square hole for the PID cut, and another hole for an on-off switch, just to isolate everything and make sure it's off. That's a self-illuminated switch too, by the way. The rear is going to be just a repeat of the front, and at the rear I'm going to fit a 240 volt socket so I can plug in my hot plate, and I'll have to make sure that the rear plate there is well and truly protected electrically, so I've got a big rubber grommet to make sure that there's no contact between any wires and the case. And yes, I know that this has to be well earthed, so we're going to take care of that as well. Oh, and I made a nice little front panel as well on the laser cutter, and I've got my temperatures marked on the bottom of that. So the Parker phosphate, we need to set that to around about 96 degrees, and the oil, it's called a dry touch oil. That's the secondary treatment to make sure that the Parker phosphate doesn't flash corrode, and that needs to be set to about 60 degrees centigrade. So that's all going to be held in place, well, mainly by the hardware, but also I'll use some double-sided tape. And of course we get the whole thing powder coated to make it look pretty. I think I'll do it in, well, maybe a wrinkle black. Wrinkle black would look good. Now, just by good fortune, I found some of this perforated aluminium sheet in amongst my scrap, and I'm going to use that for the back of the box, mainly because it's going to allow a little bit of ventilation to pass through the box itself. So I can use my laser cut front panel there as a template to mark out the shape that's going to be exposed at the back of the tube, and then we just need to fold over some seams or lap seams to go on the inside of the box. Okay, I think this stuff's already powder coated, so what I need to do now is add on like a 15mm wide lap seam both sides. The bottom edge will be cut exactly to the line, and I'll need to be a bit careful to get these radii correct. And then we just got to carefully fold this so it fits inside the box. I'm just going to cut this well over size, because the big problem is you've got to distort the waste to do your cut, and I don't want to distort this piece here, so it's going to be a bit of an issue with this cut here. So once you've got most of your waste off, you can go around and trim the remaining piece there and it'll curl up out of the way without any problems. You can see that waste bending down out of the way there now. Even now I'm being a little bit cautious, just staying a bit clear of the line. I can sand or file this to make it right. Okay, so there's our back panel with our lap seams on either end. What I'll need to do is to cut in to the tangent point on that rounded corner and leave the round intact this time. You can see with this one, because the front panel was going on, I didn't worry about that, and I just notched out the complete corner. Can't do that with this one. Yeah, a bit tight at that corner, but that's alright, I can trim that. So what we need to do now is just cut away to the tangent points. I'm just going to do that with the snips. And because this stuff is perforated, I don't have to be terribly accurate. I mean, if this was solid stock, I would. But with so many holes in it, I doubt we're going to notice. So I'm just going to trim that at 45 degrees. So you get the idea. So we'll do the same here, and then we can just do a little bit of trimming and filing until it looks tidy. Of course, it all goes wrong when you bend it. Because if you don't allow for the thickness of the material, it just, it's no way it's going to fit. It'll either be too tight or too loose. I just went over the belt sander and I trimmed these corners as close as I can get them by eye. We won't know for sure until we've done these two bends and get it inside the box whether we got it right or not. So we might need to do a little bit of trimming. But the goal is to have this sort of fit in nice and snug all the way around the edge. And once again we'll fix this with a couple of self-tapping screws at the side there. This is my shop-built DIY hydraulic press brake. It's not quite as easy to use as a normal sheet metal brake, but it has the advantage that you can insert different types of formers into this moving assembly here. So you can do rounded bends, you can deal with slightly thicker material in some cases, but it has the problem where it's difficult to judge exactly how much of a bend you're putting on your stock. So what I've done here is I should have actually fitted a depth stop, but I didn't get around to doing it, so I just put a machinist jack at this end, and I've done a test bend in this piece of stock here to get that exactly 90 degrees, and that allows you to do repeatable bends. Now, the chances of getting this to bend exactly to fit inside that piece of square tube is going to be minimal. If you're doing lots and lots of bends, you'd eventually dial it in and get it right. But when you've gone to this much trouble to get that, cut and fitted to the tube, you really want to get it right first time. So one trick you can do is to get a piece of the same stock and mark out your bend lines. Doesn't matter how long it is. The important thing is that the distance between these tape lines is the same as the marking out you've got on your piece that you're wanting to bend. And then do your first bend and then see how it looks, and you sort of need to be consistent with the way that you put it into the press. So in this case I'm going to put the line directly underneath the bending die, and I'm having the seam facing outwards. So we'll bend that 90 degrees, and then you sort of try it. So we'll put that inside the tube there, and then you've got to sort of work out where you need to do the other bend. Now if you bend right on the line, it won't fit, it'll be too big. You need to bend back slightly inside the line to allow for the thickness of the material, which in this case is about 1 millimeter. So let's do another bend and we'll just try it. And you've got to sort of keep an eye on how much material you've allowed when you do the bend. So I'm going to put this once again with the seam facing outwards. But I'm going to come back inside the line. I know it's hard for you to see that, but I've got about 1mm showing. So I've got about 1mm of material extra, if you know what I mean, on the seam. So we're bending back inside the line. Now, I'd rather have it too loose than too tight. If it's too tight, we've got nowhere to go. So probably allowing a bit extra there. So we'll just try that. And this is called bend and pray. Alright, so that's not bad. It's sort of not snug, it's sort of fitting in there okay. So that's the trick. Now, if you've done your piece of scrap and you're happy with it, you just go ahead and bend your other one the same. But once again, it's no guarantee. So let's see how we get on. So I've got that set up right under the die. So you can see the line just showing there on the edge of the die. So there's our first bend. And we've got to try and replicate what we did with that bit of scrap. So here we are, we got the line and I've got about an extra millimetre of material there. Maybe a bit less this time. Let's see how we go. Cross your fingers. Just dressed a little bit on the belt sander. There was a little tag sticking out on two corners there which stopped it fitting in neatly, and push it all the way in the tube and then press it back out again against the bench, and it's fitting nice and flush at the front there. So I'm happy with that. We're going to drill some fixing holes in the side here. I'll probably put a little right angle bracket top and bottom just to make sure that that doesn't flex and bow when we disconnect the power cord from this. So we're going to go ahead now and get a hole drill in here for the grommet, get our power receptacle fitted, and get the front plate ready by cutting out the holes for the PID controller and the power switch. Got to be close for comfort on that one. Okay, front panel done. Just get this in the box now. Here's a quick mock-up of what this is going to look like when it's done. I still have to break this down now to do the powder coat on the casing. It's a bit of a shame as it took forever to put this together. But essentially I just drilled holes for all the hardware. So what we've got is the four little feet underneath, got the handle on top, front panel with everything in place. At the rear we've got our socket for the hot plate and our K-type thermocouple coming out through this bottom corner. The main power in is this white cord, and although the inside of this is going to require a little bit of messing around, essentially there are just 6 connections to the PID controller. Power switch is pretty straightforward. There are 4 connections on the solid state relay, and then we just got to couple everything to our power point on the back. So let's get this powder coated and we'll have a quick look at the wiring, how that sort of looks inside, and then we're going to see it running. Cool. Oh, there's a powder coat on. That's called a wrinkle black powder coat, and I love it. It's like that really retro scientific instrument look, and it's sort of got a nice sort of textured finish. Okay, let's have a look at the guts. Well, there's everything sort of wired up, and I've had this running in this state, and now I need to sort of jam everything back inside and get it all buttoned up. A couple of things. Remember I said this was a self-illuminating switch? Well, it's not. It must need a separate 12 volt DC supply, which I'm not going to bother about. Let's just switch it on quickly and see what this does. And what you should see at the bottom now is the set temperature in green, 96 degrees. In red at the top you'll see the current temperature of the K-type thermocouple. So if I grab hold of that and start to warm it up, you should see it get up to 24, 25, 26 degrees. Also, the red indicator on the solid state relay is showing that it's currently passing current out through the power socket at the back and onto the hot plate, which is now heating up. So everything seems to be good. Okay, I'm going to get all the guts back inside this, and then we'll do a little bit of a test with some water and see if we can bring it up to the same temperature that it shows on our display. Okay, well here it is all put together. We'll switch her on. As soon as that boots up, you'll see the indicator light come on the hot plate. Now remember, the thermostat on the hot plate is set to its maximum, so it's not going to come into play at all. And what we should see is, as the temperature starts to rise and the water starts to get up to boiling point, we'll see our temperature here reflected by the K-type thermocouple starting to increase. So let's not hang about. I'll bring you back when we're nearly at the correct temperature and we'll start doing some measurements. Alright, we're getting up to 76 degrees on the PID controller, and that little green light there indicates that the power's either passing through to the hot plate or not. And it got up to about 72 degrees and this started to click off. So it's doing its thing, it's sort of anticipating it's getting close to its correct temperature, and it's starting to moderate the current. Interestingly, this indicator light here is switching on and off. So the thermostat is not set to, or at least it doesn't override the thermostat, this control here. So I may have to put some sort of a bypass on the thermostat, so it's just full on and we're using this for our heat control. But when we get up close to 96, we should see this start to switch on and off more regularly. It will probably overshoot. It's probably going to go through to about 104, 105. Well, actually it can't, can it? It'll only go to 100 degrees centigrade, so we're boiling water. But it probably will overshoot, and then it will settle back to the correct temperature of 96. Let's see. What you're probably going to see now is these two lights are in sync. So it's off now, both of them. Okay, we're both back on again. Okay, there's our 96. Now you'll probably see it overshoot. Now water's starting to boil. Alright, well, interestingly, that's stabilized. I thought it was going to overshoot. Okay, let me get another thermometer and we're going to test the water directly. Okay, well, this is just a digital thermometer. I know you can't see the reading on that, but that's getting up to 89.7, 91.3, 92.6. 95.4. Okay, it's overshot 96. It looks like we're sitting at about 97.7. So what I can do is calibrate this. Once I know what the error is, I can account for it here on my temperature setting, and I should be able to get to within 1 or 2 degrees easily. Now you're probably saying, why would you bother? I mean, 96 degrees is almost 100, just boil it and be done with it. But the point was that sometimes you don't want boiling point, you want sort of 40 degrees, 70 degrees. You might be making your own cheese or yogurt, God forbid. but it does allow you to set a fairly precise temperature and then not worry about having to continually fiddle with this knob to try and get it right. So I'm counting that as a win, and you'll see this come up in the next video. We're going to do the actual parkerizing process on this tool that I made. But that is going to have to wait, because you know what? I'm going on an overseas holiday to UK and Europe, and it's in the grip of a heat wave at the moment, so that's going to be fun. I'm going to be away for 6 weeks, so I won't be doing any more videos for that time. I am going to do some stuff on Instagram, but I promise no selfies, unless of course I come across some beautiful German supermodel like this one. Anyway, I'll catch you on the next video, couple of months' time. Thanks for watching.